Moving on to section P.3. So this is going to be dealing with radicals and rational exponents. So radicals are going to be pretty much an extension of what we had for exponents. So this kind of complements our last section. So we're going to look at evaluating roots, simplifying radicals and roots, rules that we have for simplifying, and then adding, subtracting with roots, rationalizing denominators, and then some work with rational exponents. Okay. So in general, if I have something squared, it equals some sort of real number. So b squared is going to be some sort of real number a, where b is going to be what we call the square root of a. So as an example, if I took 2 and I square it, I would get 4. So we would say 2 is the square root of 4. So the definition of what we're going to call a principal square root, because there's technically 2 square roots, if a is a non-negative real number, this number right here, if it is a non-negative real number, so we mean positive or 0, then the non-negative number b, which would be this 2 here, there is a non-negative number b such that b squared will equal a, denoted by b is equal to the square root of a. So we would say that 2 is equal to the square root of 4. And this is what we call the principal square root of a. So 2 is the principal square root. Oops. Square root. Square root of a negative number is defined is undefined in the real numbers. Basically, I'm saying that there isn't something that I can square that's going to give me a negative 4. Because if I take 2 and square it, that's positive 4, so that doesn't work. If I take negative 2 and I square it, that becomes positive 4 again. So that is also not equal to negative 4. So in the real numbers, negative numbers do not have a square root. We also have a negative root, but we're going to look into that a little bit later. Actually, kind of see a little bit of it right here. We just want to evaluate the following. So what we're looking for is what number squared would give me 81. And then the answer to that would be 9. Square root of 81 would be 9. So here the negative is out front. So if you just look at the 9 by itself, oops, not what I want. We're looking for a number squared that's going to give me 9, which in that case would just be 3. So because we have that negative here, negative 9, or negative square root of 9 is just going to be negative 3. The negative's out front. So here we have the square root of 36 plus 64. So we can't break up the square root. Later we can do that, but if we add that together, that is just the square root of 100. And what number squared is going to give me 100? Well, that's just going to be 10. And then the square root of negative 81. So we can't do square roots of a negative number, so this one is undefined. All right, so take a moment and just try that again. So you have square root of 16, negative square root of 144, the square root of negative 169, and the square root of 0. Okay, so hopefully you took a minute, you worked on the worksheet. So we went with the square root of 16, so what number squared is going to give me 16? So if you're not sure how to do this, what you could do is go into your calculator and just start squaring whole numbers. So 1 squared, well, that's just going to be 1. 2 squared, well, that's 4. 3 squared, that's 9. 4 squared, well, that's 16. So here we'd say B would have to be 4. So the square root of 16 is 4. Here we got negative square root of 144. Just remember that negative is out front. It's not inside the radical or the square root. So we kept going. 5 squared is 25. 6 squared is 36. And you might want to keep the list somewhere that I'm making because it'll be helpful later on. 7 squared is 49. 8 squared is going to be 64. 9 squared is going to be 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. And just because this is a common one too, 13 squared is 169. Usually don't go more than this. Usually 12 is the maximum. But we see here, well, if I take 12 in the square, I get 144. Square root of 144 would just be 12. The negative is out front, so my answer here is just negative 12. So negative square root of 144 is equal to negative 12. So we got a square root of negative 169 because we got the negative inside the square root. Trying to do a square root of a negative number. This is undefined. All right. So if you didn't quite get this one here, square root of 0, that's fine. I kind of left this one off for you to think about. So there's only one number that I could possibly square that's going to give me 0, which is 0. This is okay because we said that we wanted to do square roots of non-negative integers or non-negative numbers. So this is non-negative. 0 is not negative. So when we say non-negative, we mean 0 or positive numbers. So the square root of 0 is just 0. Okay, so here's some terminology. I try not to say it, but it just kept rolling off the tongue. The square roots are part of a set of operators that we call radicals. So radicals can be square roots, they can be cube roots, they can be any root. So an nth root, so we're saying it's like it could be a 4th root, a 5th root, a 6th root, a 7th root, it could be a 1,000th root. The symbol N, and then you see the little radical sign. This is called radical. And the expression under the radical is called the radicand. Radicand, sorry. So the symbol, this one, and I can keep making more and more of them. We call these all radical signs. And if I stick a number in there, we can refer to these as radicals. And what we'd have is the 4, 27, and the 64. Are what we call the radicand. Radicals are also exponents. So I have here that the nth root of a is just simply a to the power of 1 over n. So if I have a square root of a, that's just the power of 1/2. So if I had a 6th root of, say, 7, I can rewrite that as 7 to the power of 1/6. If I had the 3rd root of, say, 27, like I have over here, I would just say 27 to the power of 1/3. And if I just had a square root, 15, well, I can just rewrite that as 15 to the power of 1/2. So this is why we're also going to talk about not just radicals here, but we're going to talk about rational exponents, because when you have a radical, you can write it so we have something that has a rational exponent. So when we talk about a rational exponent, Just a reminder that rationals are going to be integers and quotients or fractions. Of integers. One of the nice things about this is that because square roots are essentially exponents, rules of exponents can be applied to roots, radicals. All right, so just a few more little rules here, just ways that we talk about this. So if we want to simplify the square root of a squared, so what we're going to do is that if I have 9 and I want to find a number square that's going to give me 9, I actually have two choices. 3 would work, and -3 would work because either one of these squared gives me 9. Really, -3 and 3 are square roots of 9. Three is the principal root because that's the positive one, and -3 is the negative root. This goes back to some things we're going to talk about in algebra, but we like it that when I have functions of certain kinds, which we're kind of getting into this, that when we have functions, we like it that if I put a number in, I only get one answer that would come out. So that means that for 9, I really only want to be worried about one root for the most part. Later on, we care about both roots. So like I said, this might seem silly. Sometimes we do this, sometimes we don't use these rules. Hopefully we can just work our way through when we need them. But what this means is that when I have a number that is squared, because technically 9 is just 3 squared, but also -3 squared is also 9. We want to make sure that if I do the square root of a square, that it comes out to a positive answer. So the square root of a squared is going to be the absolute value of a. And the reason we have that is, like I said, now that if I have 3 squared and I take the square root of it, what I should get back is 3. And if I had -3 squared, what I want to get back is 3. And the reason we do that is to guarantee that when I do the square root of 9, the only thing I'm going to get back is that positive 3. So that's all that's really doing is just ensuring that we keep principal roots. Where this is really going to shine is when we're dealing with variables instead of actual numbers. So if we want to evaluate the following, the square root of 3 squared would just be 3. The square root of -3 squared, like we said before, would also be 3. Now, negative square root of 3 squared would just be, there's a negative there. So we know the square root of 3 squared is just 3. So that's negative times the 3 or just -3. When the negative's out front, we can have a negative. So here, remember that the -3 is squared. The -3 is not squared in D. D is basically saying I have a negative here. And it's the 3 is the only part that's being squared because without those parentheses saying that negative's in there, we're saying that negative is on the outside. This is really saying that I have the square root of -9, which is the square root of a negative number that is undefined. If A and B represent non-negative real numbers, then the square root of A and B is equal to the square root of A times the square root of B. And Square root of a times square root of b can be combined in the square root of a and b. So where this comes from is that one of our rules of exponents. And I have it down here as well, basically said that if I had two numbers multiplied together and I raised that to a power, well, then we can distribute that power across, right? It also means vice versa. I can go backwards. So I could go this direction with it, or I can go this direction. Well, remember that square root are just exponents. So what's happening here is if I square root of a and b, that's the square root, that's just a times b raised to the power of 1/2, which means we have a to the power of 1/2 times b to the power of 1/2. And a to the power of 1/2 is just the square root of a and the square root of b. So it's really just using that rule of exponents and then that concept that radicals are really just representations of exponents. This is an important rule here because we use this to simplify square roots. All right, so we want to simplify the square root of a 9, the square root of 9 times x. So remember, we have this rule. A times b is just the square root of a times the square root of b. That means that I can change it to the square root of 9 times the square root of x. Now we know the square root of 9 is just 3. Now that square root of x, we have to go back and talk about that. We also had another rule that said that if I do the square root, oh wait, nope, that one can't change. We'll leave that one as is. I was looking at A there, but no, that's where we stop on that one. I'm sorry. B here, that's where we have to use another rule. But remember, not only can you go this way and you take the square root of A and B and break it up square root of A, square root of B, I could also go this direction, which I can do here. So square root of a times b, or sorry, square root of a times square root of b is just square root of ab. So it means the square root of 3x times the square root of 12x can be combined into 3x times 12x. So that is just 36 times x squared. Part of simplifying is, like we've seen before, is we're trying to eliminate as many operators as we can, try to condense things as much as possible. So we don't have two radicals anymore. We only have one radical, but I might be able to make that radical disappear completely if I keep going. If I go back again, I can break this up into the square root of 36 times the square root of x squared. So the square root of 36 is just 6. Now we need to talk about the square root of x squared. So if you remember, we had this other rule that said the square root of a squared was absolute value of a. Well, if we just replace a with x, that means we just have 6 absolute value of x instead of having 6 square root of x squared. If you have something like the square root of an x squared, bear in mind that you can rewrite that so it's just an absolute value of. All right, so like I said, we're building into simplifying square roots is what we're, all the rules basically simplifying square roots as we can get right now. So simplifying square roots uses the products to rewrite the radicand so it will not have any square factors. There was a typo there. Below are steps to simplify a square root. You want to first find the prime factor of the number inside the radical sign. So we'll talk about what that means. We want to group the factors into pairs. So anything that's a pair, like x squared or 6 squared, that's something that if I take the square root of it, I'd basically get the number back. We want to pull out any integer outside the radical sign for each pair and leave the other integers that could not be paired inside the radical sign. And our last step is multiply all the integers outside the radical sign and all the integers remaining inside the radical sign to get your final answer. It might sound like a lot, but I promise it's not going to be that bad. So the best way to do this is just to do it instead of talking about it. So we have square root of 75. Now, if we want to break down that 75, oops, a second, make sure I don't miss one here. So 75 is really just the square root, or sorry, the 75 here, square root of 75 would just be square root of 5 times 15. We're going to break that down further because we want what we call prime factorization. So I just want to write all the prime factors. So 15 is just the product of 3 and 5. So we can say that 75 is just 5 times 3 times 5. Or it's 3 times 5 squared. So I'm going to do this a little differently in each one, but this is one method. So we have a square here. We have a 5 squared. Well, we have this rule that says that I can break this up. What I want to do is that if I have anything that is a square under a square root, I want to separate that out. Because now, square root of 5 squared, we know is just 5. And then we just keep that square root of 3 because there's nothing I can do with it. But this right here would be the simplified form. But really what we're trying to do, especially when we have not just the variables, but we have just numbers under the radical, is that we want to take that number and we want to break it down. And if we have anything that's a square in it, we like to be able to pull out those squares. So simplifying is just this. It may not look more simplified. This the rules of simplifying radicals, if I remember correctly, go back when we had to use like slide rules and things like that. So it's kind of an archaic leftover from a previous time. But we still need to know how to do it because this is what your homework wants you to do. And this is what people are going to want to do in future math classes. Let's do this again. So I have the square root of 216. So 216, we could break it down. That's divisible by 2. So we're going to break that to 2 times 108. And 108 is also divisible by 2. So we'd have 2 times 2 times 54, because 2 times 54 gives us 108. So 54 is also divisible by 2. I could break this down further into 2 times 2 times 2 times 27. Now 27, I can tell you this, 27 is actually just 3 times 3 times 3. If you want to do it step by step, you're going to get 2 times 2 times 2 times 3 times 9. And then if we break down that 9 even further, you get 2 times 2 times 2 times 3 times 3 times 3. So another method that we could use is that we have a pair here and here. We have 2 2s and we have 3 3s. So we have a 2 squared and we have a 3 squared, but we also still have a remaining 2. We still have a remaining 3. Okay. So what I see sometimes people just pull out the 2s, but let me show you what's going to happen here. So we got a square root of a squared. We have a square root of 3 squared. And then we can also do a square root of that 2 times 3 that's left over. So 2 squared we know is or so square root of 2 squared is just going to be 2. The square root of 3 squared is just going to be 3. And then we still have that square root of 2 times 3 because we had two numbers that we couldn't find pairs for. So this is just 6 square root of 6. To show you an alternate way to do B, sometimes I see doing this instead of doing all this breaking up. So it says 2 times 2 times 2 times 3 times 3 times 3. Some people just find it easier to go through here and go, oh, I have 2 2s, I have 3 3s. So those are going to be brought out in front because eventually when I do that square root, that 2 is going to be out here and that 3 is going to be out here. And then we have this 2 and this 3 are still left over inside the radical. Once again, 6 squared square root of 6. So some people, like I said, they just like to find the pairs and just pull them out front. Or you can sit there through the work and go, okay, well, I have a 2 squared. I need to break that up as a product under a quotient, under a radical, like I said here in red. So C, be similar to what we did before, is I have square root of 5x times the square root of 10x. I can combine that into the square root of 5x times 10x, which is going to be the square root of 50 times x squared. Now with 50, that could be broken down to 2 times 5 times 5. And then we have that x squared. Once again, because I have a pair of 2s, or pair of 5s, we really have a square root of 5, or square root of 5 squared times x squared, and then we have that 2 left over. So what's going to happen is that square root of 5 squared, and then we're do times a square root of 2 squared times the square root of that 2. So 5 square root of 5 squared is 5. Square root of x squared is absolute value of x. And then square root of 2. So typically what we like to do is we'll put the 5 and times the square root of 2 next to each other, and then the variable we'll put at the end. Okay. So quotient rule, if A and B are non-negative real numbers, and B is not equal to 0, because if B is equal to 0, it's undefined, right? Because I'm dividing by 0. The square root of A over B is the square root of A divided by the square root of B. And once again, this goes back to rules of exponents. If I have A over B to the power of n, then we can distribute that n to the top and to the bottom. So if I have absolute value of A over B, well then that's just going to be A over B to the power of 1/2, which means we have A to the power 1/2 over B to the power 1/2. And we know that this 1/2 is just going to convert back to a square root. We can break up a square root over a product and over a quotient. Okay, I'm going to simplify these square roots. So square root of 25 over 16. Well, I could break that up into the square root of 25 divided by the square root of 16. Square root of 25 is just 5, and the square root of 16 is just 4. Helps us take some that look a little more complicated. It makes it a little easier for us to simplify. If I have the square root of 150x squared over the square root of 2x, Well, remember, I can go backwards and I can combine that. So it's just a square root of 150x squared over 2x. So now that I did this and everything's under the radical, I can start simplifying. So 150 divided by 2. Okay. Will end up being 75. And then we have an x squared divided by x. This is going to leave us with x. So we have the square root of 75 times x. All right. And we already did the square root, or sorry, we'll do it here. So we already had simplified the square root of 75 earlier. So that would have been 5 square root of 3. And then we're just doing a square root of x. So that's not an x squared, it's just x. So we're just left with a square root of x. So this might actually just be 5 square root of 3x. All right. That was quite a bit to go through, but now you finally get to go back to your worksheet. So pause this and work on these, but you just have a few of these, just try to simplify as much as you can. So we have square root of 60 times square root of 5, and then you have the square root of 3 times 4 squared over the, 3 times 4, x to the fourth power divided by the square root of 48. Then you have the square root of 72, a to the fourth divided by the square root of 2a. My guess is these two might be a little tricky for you, but try it out. And we'll come back to it. All right, so hopefully you had a chance to work in these. Don't worry if you didn't get something working out correctly. That's why we're doing this. As I said before, mistakes are good. We learn from mistakes. So this is going to be combined into 60 times 5 under the radical. So if you wanted to, you could just multiply that. But remember, we're going to have to break it down anyway to see if we got any multiple of prime factors. So if we take 60, well, 60 is divisible by 5. So 60 itself is just 5 times 12, and then we still have that other 5 here. And 12 is divisible by 3, so 5 times 3 times 4 times 5. That's 5 times 3, and then 4 is just 2 times 2. So 60 times 5 can be broken down into 5 times 3 times 2 times 2 times 5. So let me rewrite this. We see that we have 2 2s, and we have 2 5s, and then we have that 3. So because we got those 2 2s, I can pull those out front because I'm just gonna, when I do the square root, I'm just gonna be left with this 2 2s just becomes a 2 on the outside of the radical. 5 times 5 just becomes a 5 outside of the radical. And the only thing left inside the radical is that 3. This is 10 square root of 3. All right, I'm gonna get my arrows out of the way here. Now with B, we can take that quotient and we can combine it under the same radical. So that would be 3x to the fourth divided by 48. So 48 is also divisible by 3. It's going to give me 16. So the 3 divided by 48, I can take that fraction and simplify it. So now it's just going to be x to the fourth over 16. Well, that's going to make this easier for us. Let's break that back up again. So we have the square root of x to the fourth and the square root of 16. So we know the square root of 16 is 4. But we're going to take a little extra time with this x to the fourth. So remember, that's x to the fourth raised to the power of 1/2. Just bear that in mind. So what would happen here is that this will end up turning to a x squared. Okay. So this is my voice there. So C, same thing, we combined it. So we got 72 a to the fourth over 2a all under the same radical. We need to start simplifying that as well. So we got 72 divided by 2, which is going to leave us with 36. We have a to the fourth, and then divided by a to the first power, leaving us with a to the second power. So this one would have been the square root of 36. And we have a cubed. Well, that can break down to a squared times a, or a to that first power, right? Because if I multiply those, I'm going to add those exponents. So what we have here is the square root of 36, the square root of a squared, and a square root of a. 36 is going to be 6. The square root of a squared is going to be absolute value of a, and then we still have that square root of a. All right, so you've got to be careful sometimes when you have those powers. So here, because we had an x to the fourth and then I halved it, we just get x to x squared. So we don't have to worry about square roots there because x squared is going to stay positive. Here we have an a cubed. If I do the square root of that, that means I have to take off an a squared and separate it from the other a. So it ends up turning into a square root of a cubed turns into absolute value of a times square root of a. And here, because I don't know a is positive or negative, I need to make sure I keep an absolute value of that a. Subtracting square roots. So 2 or more square roots can be combined using the derivative property provided that they have the same radicand. Such radicals are called like radicals. So what this means is that if I had the square root of 3 plus the square root of 2, these are not like radicals. And we can't combine. However, I had 2 square root of 3 plus 5 square root of 3. What we have here is now we do have like radicals. So because of that, we treat it like if we had 2x plus 5x. Well, how many square roots of 3's do I have? Well, I have 7 square root of 3. And this is what we mean by like radicals. So we want to add and subtract as indicated. So we're going to start easy here. If I have 8 squared of 13, 9 squared of 13, that's a like radical, the same radicand there. So 8 plus 9 is 17, so 17 square root of 13. If I have 17x minus 20 square root of 17x, well, that's just going to be 1 minus 20, so minus 19 square root of 17x. All right. So take a minute, try some of these on your own. So A is pretty straightforward. B, we got the square root of 20. Think about how can I rewrite that square root of 20 so it is simplified and see if maybe then I can combine my radicals. And then C, similar thing is that we got the square root of 75 and the square root of 14. We want to see once again if I simplify those square roots, is this something that then I have like radicals and can combine? Okay. So hopefully I had a minute to work on this. So here we have a 3. The only thing that is like a like term or radical or anything like that would be this -1. So 3 minus 1 is just 2. Then we have a like radical here. We have 2 square root of 7, 3 square root of 7. So how many square roots of 7 do I have? I have 5 square root of 7. So that one's simplified. Okay. So we haven't done this one yet, but we have the square root of 20 plus 3 square root of 5. We need to figure out what the square root of 20 is. So 20 is just 4 times 5, which is 10. 2 times 2 times 5, which means that I can just break this down into 2 square root of 5. So this is actually just 2 square root of 5 plus 3 square root of 5. So sometimes it might not look like you have like radicals, but if we just do a little simplifying, we may see that we in fact like radicals. Once I get to this point, well, how many square roots of 5 do I have? I have 1, 2, 3, 4, 5 square roots of 5. Okay. So I already did some of this work for us because we already did this earlier. We know what the square root of 75 is. So this can be rewritten as 3 square root of 2 minus 2. And we know that the square root of 75 is just 5 square root of 3. Minus 1 square root of 3 plus 3 square root of 7. And then we have this times square root of 14. So if I look at that square root of 14, or actually just that whole term altogether, yeah, let's do that instead. So I'm going to change this just a little bit. We have a radical times a radical here. So this is 3 square root of 7 times 14. So if we go back here, simplify a little bit more, we have 3 square root of 2. This 2 and this 5 can multiply together. So then we just have 10 square root of 3 minus 1 square root of 3. And then here we have plus 3 square root of 7 times 14. So 14 is just 2 times 7. So we have a 3 square root of 2. This is a like term, and this is a like term. So negative 10 square root of 3 minus 1 square root of 3, it's just minus 11 square root of 3 plus 3 times. Now here we have a 7 times a 7, right? So this is just the square root of 7 squared times 2. So that radical that we have that was the square root of 7 times 2 times 7 can be rewritten as just 7 square root of 2. So now we have 3 square root of 2 minus 11 square root of 3 plus 21 square root of 2. Now we have a like radical again. So the 3 square root of 2, 21 square root of 2 is just going to be 24 square root of 2 minus 11 square root of 3. Yes, that one was a lot of work. Don't tend to see that a whole lot, but it will pop up here on occasion.